Thank you for being here, and it's a really nice opportunity to present here our research about reversing Golang binaries with Ghidra. I did this research together with one of my colleagues, Albert, but unfortunately he couldn't be here today, so I will present the topic to you now. Just before we start, I quickly want to introduce myself. I work as a senior threat researcher at Cujo AI. I've studied mathematics, and then my master's I did in advanced cryptography. And I was working at security companies and also different financial institutions. And my main focus is malware analysis and reverse engineering. So a few words about why we did this whole research, how this whole thing started. At Cujo AI, our team is focusing on IoT malware research, analyzing botnets and different IoT malware families. And we realized that we see more and more samples written in Go, not just IoT malware, but malware in general. And the issue is that reversing Go binaries is challenging. First of all, these binaries are usually much more larger than binary written in C, for example. We will see examples for that later on. And they have an unusual string handling and other issues that we really have to consider. In our team, we use Ghidra as a disassembler, which is an open source tool released by NSA. And compared to IDA Pro, for example, it's in early stage writing scripts and different tools for ADAR analysis. So there were only a few scripts available to help our problem to analyze Golang binaries. And our goal was to find some way to make it easier, to make our lives easier. So that's why we started to work on how could we make this analysis much more effective. So basically what I will explain in this talk today is what we need to know about the Go language, what we need to understand there, what the different features Ghidra has that we used in our project, and then I will introduce the scripts that we wrote, and those are also available on GitHub. So if anyone needs these scripts, want to use it or improve it or just collaborate, then you can find it and use it for your own analysis. So a few words just quickly about Golang. This is a language which was developed by Google and made available to the public. Now we are at the version of 1.18. In our research, we were mainly focusing on versions up to 1.15 because most of the malware families that we analyzed are written in versions up to 1.15. But I will also mention some of the changes that happened since then between 1.15 and 1.18. And there are many different researches and questionnaires which shows that the Golang is getting more and more popular, not just among malware developers, but for developers in general. It's very easy to learn language, very simple and with clear documentation, and probably the biggest advantage of this language for example, malware developers is this the cross-compiling feature of Go. So you don't have to maintain different code bases for Linux, Windows, Mac, and whatever. You just have one code, and then you can compile it for the different architectures that you want to use it. And this is, for example, in case of botnet families, this is very useful for the malware developers. They then compile it for ARM, x86, whatever they need. They just have one code base, and then they can use it on many different devices. So that's why it's, I think this is one of the main reasons why it's very popular, and also it's really simple, like a scripting language. It's easy to write in Go. And so, for example, if we look at the malware families here I mention a couple of recent families, and also research from the Palo Alto research group and also Integer. they showed that the number of malware families written in Go increased dramatically in the last couple of years. It's not just IoT malware, not just Linux malware, it's also and mainly Windows malware, but in our team we are focusing more on Linux binaries. So, sorry. Now I will only talk briefly about two families because we used samples from these to demonstrate the examples in this talk. And on every slide you will see which exact malware sample we will be using to show that specific feature. So if anyone wants to later on play with it, try out, do the exact steps to understand what we were doing, then it's very easy. You can either download the malware samples from VirusTotal, and there are non-malicious samples that we used and upload it to our GitHub repository, so you can also use those. So the first one that you will meet during this presentation is the EcoRX ransomware. This was first discovered in 2019, but it is still active since then. It used both brute force and different exploits to attack mainly QNAP NAS devices. And over the years, it added new and new exploits to its toolset, and for the first version there isn't the decryptor available, but unfortunately for the later versions we don't have those yet. And the other malware family that we use for this research is the Kaiji botnet. This is named after a manga series, and it was first discovered early this year. It's fully written in Go from scratch and spreads using SSH brute forcing. Basically, it is get installed into a specific location with process names that looks legit, and then maintains persistence through various solutions. And then basically it copies the rootkit module and run it every 30 seconds. And obviously it will then initiate DDoS attacks. So let's talk a little bit about Go binaries. The one thing is the static linking in Go. So by default, these binaries are statically linked. That's why the huge size of a Go binary. And it means that all the necessary libraries are included in the executable, which means that it can run on every system without any dependency issues. It will have everything within the binary that it needs to run. But with this large size also comes with some drawbacks, like, for example, the malware distribution is difficult. I'm talking about our IoT malware, but obviously where we don't really have enough room for such large binary, it won't work. But that's one issue. Also, sometimes AV products have some issues detecting these Go binaries. And also, reverse engineering is much more difficult when we have to look at such a huge binary. And I will show examples of what you have to face when you do reverse engineering. So let's start with simple hello world examples. We will compare a hello world written in C and hello world written in Go. Now we are talking about the unstripped binaries, and basically what is interesting from this slide is only the size of the files. So if you create a simple hello world in C and also you create one in Go, you can see that the Go version is like 2 megabytes. That's huge compared to the 16 kilobytes of the C binary. And also, if you upload it into Ghidra, so I'm not sure how much you can see from this, but I tell you what the main thing that you have to look now. There is a list of functions that are included in the binary. And in case of the C, there are 19 functions. That's very easy. You can just go through that and then see what this binary is doing. But in Go, there are 719 functions. So that's crazy. So you have to find something interesting among those functions. And what is even a bigger problem, that usually we don't see these clearly, these function names, because most of the cases these malware flies are stripped. So it means that the debugging symbols are discarded. The size of course will be reduced. That's very nice. And but there will be no function names, no variable names, and it's more difficult to debug and reverse engineering. So when you cannot read what this function is doing exactly, that makes our work more difficult. And but if you take a look at the same examples, but here we stripped the binaries in case of Go with the ld flags -s parameter, it's reduced from 2 megabytes to 1.3, which is still large. So if we look at the functions again, now we don't have the 1,700, but we still have 1,000 and more than 1,100 functions, and we don't have the function names. So we can see that there are 1,000 functions, all with some numbers, and then here you go, let's try to find out what's going on here. So what we were trying to understand, if we could recover these function names, how can we do it? And obviously, how we came to this idea, we already knew that this can be recovered. So if you don't use, for example, Ghidra, but you use IDA Pro, the latest version can already do it for you easily. But here we are talking about how to do that with Ghidra. Just for comparison, if we look at the main function within the disassembler view of Ghidra, then you can see on the left side the unstripped version, on the right the stripped version. It's not too difficult. Okay, now we don't see the name of the function, but it's just a few lines, so it's still easy to understand. But in case of Go, already the main function, which is supposed to only print hello world, is much more complicated than in C, where it's just one line. And when it's stripped, we don't even have the function name, don't have more information here. So what we were trying to do here is figure out how we could recover the function names. And the first step we did, we tried to look for the function name within the binaries. So on the left side, what you can see is looking for the main function name within the unstripped version. In case of Go, the function name that we were looking for is main.main. And on the right side, you can see we were looking for the same in the stripped versions. In C, the main string just simply disappeared from the stripped binary, but in Go, we could still see main.main, which gave us some kind of hope that we can recover it. So what we did here, we loaded the binary into Ghidra and tried to look for the main.main string. And when we looked at the memory map, we saw that it's in a specific section called Go PCLN tab. So the next step was to figure out what this section is about, what can we know about this section, and how what kind of information is stored there. And it was pretty easy. So from Go version 1.2, there is a very nice documentation. The link is on the slide if someone is interested in more details about how the PCLN tab structure looks like. It usually, always, it starts with a magic value and then 20 bytes following by instruction size quantum and the pointer size. And then what is really interesting for us here is function addresses followed by the function metadata pointers. So for we have an address of a function and then a pointer to a function metadata table. So let's take a look at the function metadata table. Here it starts again with the entry point of that specific function. And then, among other information, there is an offset to the function name. So where can we find the name of that specific function? This changed this year in Go version 1.16 and 1.18. Our script is already updated for 1.16 and will be shortly for 1.18 as well. So basically we have all the information there still, but the function name offset and also this function metadata table was moved to somewhere else. But I won't go into details, but it's still there, so we can just find it using this information. The nice thing about Golang is that everything is nicely documented. You can just look at the source code and find what you need. So, for example, here you can find the magic values that are used by different versions for the Go PCLN tab, and also how to check, how to search for this structure, and for every single version when some changes were made, there are it will exactly show you how to recover the information that you need. So basically you just need to do the same in scripting for Ghidra, but these are exactly the same steps. So you can see here the version 1.2, 1.16, 1.18. It will tell you how to search for the function name tab, how to search for the file tab, how to search for the function metadata table. And here, one side note, so during our research we were focusing on Linux, but for Windows there is no specific section called Go PCLN tab, so in our script we are looking for that section, but in Windows this structure is still there, so what you need to do here is looking for that magic values and all the bytes that are following, so that's not much more difficult than in case of Linux. Here on one example, I just want to demonstrate the steps. So the idea is to find this PCLN tab structure, extract the function address, and then find the function name offset. And then you can just basically recover your function names. So here, if someone is interested, you can go through every step. We calculated it here. So first you find the PCLN tab, and then in here there is the function address. We also put it there that there is this main.main function that we are looking for, and then there is an offset to the function metadata table where you can find again the address of the function followed by the address of the offset of the function name. So this is basically what we need to recover function names here. So after executing the script, what we can see that from 1100 functions, we will get almost 1800. And now we have all the function names nicely visible. So, for example, main.main can be found. And, well, with this hello world example, it's not very interesting. But if we look at a real world example, this is an AcroX ransomware. Once you execute the script and you can see the function names, just by looking at the function names like main.write message, main.check readme, make secret, or encrypt, you don't really need to do much more to have an idea of what this piece of malware is doing. It's pretty obvious that it's a ransomware, but at least you know where to start the analysis. So just by simply recovering function names, it becomes very easy to start reverse engineering such binaries. And there were obviously some challenges. Ghidra had some issues which were solved even from Ghidra 9.1 to 9.2. So now this works much better. But for example, it can happen that you are looking for a function name, but there is no strings defined there by Ghidra, so it will just throw an error that there is nothing because Ghidra didn't realize that there is a string. So in that case, we just need to take care of it before we use that. We just have to create the string there, and then we can recover the function name. So this was the first topic, and now that we were talking about the strings, let's move to the second one where we looked into the strings within Ghidra. So again, let's start with an easy hello world example, and we look into the defined strings window within Ghidra. This is where you can find all the strings that Ghidra could extract it from the binary, and it can also be very helpful first step when you're analyzing a malware. And on the left side, you can see the C version, and on the right side, you can see the Go version. So while in C there are 7 defined strings, there are more than 6,000 in the Go version. So that's already a little bit difficult to go through all the 6,000 strings and try to figure out what is interesting for you. And what is even worse here, that this is the hello world binary, so we are looking for hello world, which is nicely visible in the C binary. But in Ghidra, even there are more than 6,000 strings, it won't find hello world for you. So the only thing that would be interesting. So let's take a look at the strings. First, we just simply use the strings utility and grep for hello to see what we can expect. And in C, that's pretty obvious, we got hello world. But in the Go binary, the problem is that you can see that we got like a huge string blob and somewhere in the middle there is hello world. Now it's easy because we know that we are looking for hello world, but when we don't know what we are looking for going through these, that is very time consuming and not really helpful, so you won't read everything line by line. So let's look at what are strings within Go. So in C, what we all know, this sequence of characters terminated with a null character. The main difference is that in Go, these are sequence of bytes with a fixed length. So they are not null terminated. And there is like a specific structure, the string structure, which consists of the a pointer to the string, and also there is an integer showing the length of the string. So we need to find these structures. And yes, and all these different strings are concatenated together to like a large string blob, and that's why when we were looking for hello world in the previous slide, we got that huge string. So that's why Ghidra has a hard time defining these strings, because it looks for characters, null terminated characters, and this is what Ghidra can handle. So the idea was to have Ghidra somehow find these string structures. And there are many different ways how these string structures can be built up. They can be statically or dynamically allocated. This is very different per architecture set, and even within one architecture there are multiple solutions, and it can change per Go version. So it's like a mess how you can recover the strings. So I will go through a few examples now. Let's start with the dynamically allocated string structures. So it basically means that these structures will be built up during runtime, and there are several different scenarios again. So if we look at the hello world examples again from the string point of view, if you look at the disassembly of the main function in C, it's very easy to read. So even if you never use Ghidra or IDA or anything, if you just look at this assembly, you can tell that it will print hello world. But for Go, it's a much bigger function. You don't even see hello world, and probably you don't, I'm not sure if you see it, but there is an H which can help. But in general, it's a much bigger mess. It's not that easy to read. So, but when you take a closer look, then you will find an address which is moved to a register, and if you follow that, you will see that there is hello world. This is how it looks like when it's not defined within Ghidra. These are just sequence of bytes, but it doesn't realize that it's a string. And then there is an integer moved to the stack, and this is the length. So basically, this is how the string structure is built up during runtime. And now we will take a look at the x86 and then the ARM architectures. So here what our script is doing, it will look for these specific instructions, these instruction sequences. So here, for example, first the string address is moved into register and then placed onto a stack, and then a string size is placed onto the stack. And that's the same for 32-bit and 64-bit almost. It works the same. And so if after we execute the script, what happens that the hello word string will be defined by Ghidra, so you will be able to find it among the strings within the defined strings window. And also, if you follow the address to the string, then it will be nicely visible. It's not just sequence of bytes, but nicely there is hello word. And when you read the code, there is already in the middle the hello word string, so it's much easier to guess what's going on there. And for example, if we look at again the EchoRX ransomware example, in the beginning we had more than 9,000 strings. Now we have even more, so this didn't help in the problem that how to find interesting strings when we have 11,000 strings. But at least when we read the code, then for example here you can see that readme for decrypt.txt, so that again something that will help by just looking at the functions and like grab some idea what is going on there. And let's move to the ARM version. I will show 2 examples here as well. It looks very similar. So first, there is one extra step, because there is a string address pointer which is moved to the register. But then it will also move to the stack along with the string size. So what you can see here, that if you follow the address, then there is a pointer which will point to the address of the string, which is not defined. And then once we execute the script, the disassembler will be much nicer, because you can see there, do not remove this file and whatever, the text itself, and also it will be defined. And if we look at the ARM 64-bit example, so this is what I have already said, that there are differences between different architectures, and also here there are differences even within one. So for example, these 2 sequences of instructions are very similar. They are doing the same, but there is in the first one the OR instruction, while there is a move in the second one. But the idea is the same. Everything will be placed on the stack, and if we find these instructions, then basically we will be able to recover all the strings that we were looking for. So this is, for example, a Kaiji example, and then you can see how the code looks like after we recover the strings. And here there are several challenges. So first of all, we have to write it for every different architecture. And as you have seen, there are different solutions within one architecture, and it's very easy to break intentionally. So you just do it something a little bit other way around, and then our script won't work. And now from Go 1.17, there is a new, so what you have seen, that everything was always placed onto the stack, and this is very unusual, how Go handle these arguments and return values of a function. Everything was always placed onto the stack instead of registers, how we used to see it. But they changed it for Go 1.17, and now they also use registers instead of the stack. So we also have to consider that. But every malware families that we have seen so far, they obviously didn't update it to Go 1.17 yet, but still we have to be able to change our script in a way that it will detect these even when we see a newer sample. So this was the dynamically allocated part. And there is this probably much easier part, the statically allocated string structure. So what's going on here? It's basically there is a part within the binary where the addresses are placed of the string pointers followed by the lengths. So these structures which I have shown in the beginning, this is just simply there within the memory. And here, to eliminate false positives, we limited the string length, so we didn't look for any integer, and also we only searched for printable characters and only checked it for in specific sections. It is not architecture specific. So what we are looking for here is we look for an address followed by an integer. And if we find something like that, then we will try to create a string there. So if you follow this example here, the first pointer was successfully defined since it is directly referenced from the code, but it is followed by a length and then another pointer and a length and a pointer, but Ghidra just didn't realize what those are. So if we take a look at the address, we can see that there are different extensions. So yeah, this is the AcroRx ransomware again. So these are file extensions that we would expect from a ransomware. So what it can encrypt or what it won't encrypt. And once we execute the script, all these pointers will be created. Also, the integer data type will be created, and all the strings will be defined. So you can see it on the define strings window, and also you can take a look at it and search for those easily. And so what are the issues here? Two very easily solvable things. So our script will look only for printable characters, as I mentioned, but it's a very easy part of the code. So if you need anything else for your research, then you can just easily change that part. And also we limited the length to, I guess, 100 now, but it can happen that you're looking for a larger string, so you can play with it in a way to find the best for your project, and also don't get too many false positives. And just some sidestep from Go. This statically allocated string structure is not only it is something that we can observe in other languages as well. So, for example, other than Go, we also seen some malware families written in Rust recently, mainly for Windows. And for Rust, it is the same. So, statically allocated string structures can be found. So, the same idea can also be applied to Rust binaries, because they handle strings the same, very similar way to Go. So you can also look for these structures. The only thing that you have to consider in which sections to look for these, but this is just some note. And here I would also like to show some of the challenges that we faced. The first one is when there are some already defined data types where we want to define, for example, an integer. And what Ghidra does, it usually uses these called undefined data types, but it still means that it's already created. So what we need to do here is, if we want to create an integer there, then first we have to remove the undefined data type, and then we can create the integer. So here, for example, our script would fail because, okay, I cannot create here integers and pointers because there are already something else then. But if we remove first the something else, then it will be easy to create what we need. So this is another example from the AcroRx ransomware, how we could recover certain strings. And another problem is when the string is already defined, because as I mentioned, how Go handles strings, they create large string blobs. And this can happen, there is a null character at the end, so will Ghidra falsely identify it as one huge string instead of smaller separate strings. So what can we do here is, so in this example, for example, you can see that there are many off-cut references to that specific string. It means that there are references to some certain parts of the string, so not the beginning, but to somewhere in the middle from the code. So if you find in the define strings window, what you can do here is to sort the strings based on the number of off-cut references, and when you see something with multiple thousands of off-cut references, then you can safely undefine it, and then you will be able to create the smaller strings. So that's also one step that we have to consider. And this is, at the moment, is not handled by the script itself, but you can do it yourself just to check these specific strings. And basically, these were the two topics that I wanted to discuss today, and just want to introduce some of the next steps. So, of course, working on the string recovery, it's a continuous work. So, for new architectures, for new versions of Ghidra, for whatever, that's something that we have to consider. As also what I've mentioned, that function return values and arguments are placed onto the stack, which is not really easy to Ghidra to handle, since these are not in registers until 1.16. There is one goal to somehow help Ghidra to handle these much better. So, because now we cannot really see what are the arguments, what is the output of a function. So it's a huge mess. But even now that these are moved to the registers, it's not perfect. So there are room for improvement. And another interesting feature is in Go is like types, like the string structure that I have mentioned before. There are different descriptions of types within the binary. There are obviously the built-in basic types, and there are some composite types. But when you write a Go script, then Go program, then you can define your own types. Like in this example from EchoRX, there is the main.info struct, which consists of a public key and the readme string. So, and this is also stored within the binary. So it is possible to recover these, which is very helpful when you want to analyze more deeply, or for example to see what is sent to the C2 server and there is a structure containing all the information, what can be sent, or what commands, for example, botnet can get from a C2 server. So before I finish my talk, I would like to mention some other researchers' work, mainly for other tools. IDA Pro is pretty good in handling the Go situation now. Also for radar, there are very good solutions. We work with Ghidra for that. There were not many, that's why we started it. And these are the files I used during this presentation. So if anyone wants to dive in deeper, like just practice Ghidra, I think these are perfectly good to start with. Some references and nice additional reading. And with all this, I would like to thank you for your attention. You can find us on Twitter, also our research group, and you can find all this, everything that I've been talking here on GitHub, so you can use the files and anything, and just feel free to contact me if you have any questions or anything else. Thank you very much.